Welcome back to the second lecture on GPUs. So today we're going to talk about the memory system of GPUs and also the concept of warps. Okay, so we're going to start with memory because memory is actually one of the most important issues for getting good performance on computers. Okay, so remember from a few lectures ago, we said that there's this big gap between the performance of processors and the performance of memory. Okay, so we can actually compute a lot faster than we can read data out of memory. Okay, and in fact, this gap has been growing over time because processors keep getting faster and they get faster a lot more quickly than the memory improves. Okay, so today, the main bottleneck for many programs is the memory. Okay, we say that many programs are memory bound because the limit to their performance is actually on how quickly they can read data. Okay, if they could read data faster, then they would also perform faster. Okay, so therefore, the way that we have of dealing with this is that, remember we said computers have a memory hierarchy. Okay, so we have different types of memory, right? And the different types of memory have different sizes and also different speeds. So if we can somehow make use of the right type of memory at the right time, then perhaps we can get better performance. Okay, so first let's look at the memory hierarchy for GPUs. Okay, so there are several layers to this hierarchy. So at the top layer, so the biggest memory is called the global memory. Okay, and then there's something called constant memory, but we're kind of going to ignore this because it's very small, first of all, and it's also kind of a subset of the global memory. Okay, so we're going to ignore this. So next we have the shared memory, right? This is quite important, and the L1 cache. Okay, and then lastly we have these registers. Okay, so now the top of level of the hierarchy. Okay, so the biggest chunk of memory is going to be the global memory. Okay, so GPUs have something like between 1 to maybe 32 gigabytes of global memory. Okay, so maybe we can actually change this 1 to like a 3 over here. Okay. Now, because it's the biggest chunk of memory, it's also, so the biggest chunk of memory is sitting farthest away from the actual processing cores. Okay, and so they also have the highest latency to the cores. Okay, so in fact, if you want to access global memory on the GPU, it's going to take hundreds of computing cycles. Okay, so like 400 to 800 cycles. So that means that in one trip to read data from the global memory, right, you can actually like do 400 computations or 800 computations. Okay, and the global memory is also limited in terms of its bandwidth. Okay, so for example, you might only be getting you might only be able to read 150 gigabytes of data out of the global memory each second. Okay, now higher end CPUs, maybe you can upgrade this number a little bit. So maybe you can make this 1 into like maybe a 7 over here. Okay, but it's a few hundred gigabytes. And this turns out to be actually not fast enough. Okay. However, the nice thing about the global memory is that all the threads on the GPU can access the global memory. Okay, so this is like a completely shared memory between all the threads on the GPU. So remember that on the GPU, we broke the threads into thread blocks, right? Now, regardless of which thread block a thread is in, right, it can access anything from the global memory. So therefore, we say the visibility, right, is going to be the entire grid of threads. Okay, so that's the biggest memory. Now we're going to go to the next layer of the hierarchy, and so this is the shared memory, and this shared memory physically it's actually located on these SMs. So remember, these SMs are like the streaming multiprocessors. Okay, and the streaming multiprocessor basically corresponds to a processor in a normal CPU, right? So it's a processor and it has many cores. Okay, and this processor has some memory called the shared memory. Okay, so the shared memory is kind of like, it kind of corresponds to the cache on a normal processor. Okay, and in addition to the shared memory, there's this thing, the L1 cache. Okay, however, the thing is that the shared memory and the L1 cache are physically implemented by the same hardware. Okay, so you have this block of basically, it's usually 64 kilobytes, okay, of memory. And you can split that between the shared memory and L1. Okay, so in fact, you can configure that at runtime, how much of the 64 kilobytes you want to be shared memory versus the L1 cache. Okay, so the L1 cache is just like a cache. Okay, so it stores data that's been recently used, and it evicts data when when you're out of space. Okay. On the other hand, the and this eviction stuff is controlled by the hardware. Okay. On the other hand, the shared memory is actually controlled by the programmer. Okay, so the programmer can decide exactly what to put into the shared memory. Okay, and now this shared memory in the cache, they add up to 64 kilobytes. Okay, so this is actually tiny compared to the global memory, right? Which is like tens of gigabytes. Okay, and then so you have to share the let's see, and the sharing is. We can split the 64 kilobytes between the shared memory and the L1 cache, and you can either give 48 kilobytes to the shared memory and 16 to the cache, right, or vice versa. Okay. Now, even though the shared memory is, or I'm just going to call the shared memory is so small, right, it's actually very useful, and it can help you dramatically improve performance. Okay, and the reason is that the shared memory is much faster than the global memory. Okay, the shared memory might have a latency of, let's say, 20 cycles or a few tens of cycles. Okay, so that's like 20 or 40 times faster than global memory. And also, it's got a lot more bandwidth than global memory. Okay, so let me actually erase this one here, because what I want to show is that the shared memory might have something like 10 times the bandwidth of global memory. Okay. Now there is a limitation here, which is that the shared memory, because it's located on an SM, right, and because thread blocks are allocated onto SMs, right, then the only threads which can see data from a piece of shared memory are the threads within a block. Okay, so the visibility is restricted to a block. So if you have another block of threads, so if I have one block of threads and they allocate something in their shared memory, then a different block of threads cannot read or write anything from the shared memory, right? They have no way of accessing this shared memory. It's like private to this block. Okay, and the same goes for the L1 cache, because again, the L1 cache is physically implemented from the same hardware as the shared memory. Okay, and the final thing are the registers. Okay, so the registers are also living in an SM, and we have actually a lot of registers. Okay, so we can have maybe like 64,000 registers per SM. Okay, and the reason is that these 64,000 registers need to be split between all the threads allocated to the SM. So if you have 1,000 threads on the SM, then actually each thread can only get 64 registers. Okay, and now these registers have very low latency. Okay, so basically you can access them every cycle. So so they're the fastest type of memory, and they also have the fastest bandwidth. Okay. However, the problem with the registers is that their visibility is restricted to a thread. So what happens is each thread can allocate memory which is stored in its registers. Okay, but another thread cannot read the registers but one thread cannot read the registers of a different thread. Okay, so the registers are private to each thread. Okay. Right, so we'll look at, so the first thing we'll look at is how to make use of the global memory, right? Because most of your data is going to be stored in the global memory because it's the largest chunk of memory, right? I mean, even if you take all of the shared memory for all the SMs and you add it together, right? So you have 64 kilobytes of shared memory, okay, let's say. Okay, and then let's say you have 32 SMs, okay? So you multiply all that together and you get like 2 megabytes of shared memory. Okay, so it's a tiny bit of shared memory. Okay, so if you want to do any real computation, we're going to have to make use of the global memory. Okay, now this global memory, right, we said that it's got a very high latency. Okay, 800 cycles. Okay, so what are you going to do? Right, so now if each thread just tried to if it performed a global memory operation and then waited for that operation to complete before it did the next operation, right, then this thread would basically run at 1/800th of its potential speed. So that would be horrible, right? So the way we get around this is that so GPUs use this technique called massive multi-threading. Okay, so what happens is that instead of just one thread, right, waiting for the entire memory operation to complete, what's going to happen is we're going to run many threads on one SM or on one core. Okay, so what's going to happen is so here, if we look on the right over here, we have several threads. So the first thread, let's say this is thread 1 over here, right? At the beginning, it starts a memory operation. Okay, and the memory operation takes a long time to finish. Let's say it finishes over here. Okay. However, because T1 is going to need to wait such a long time, then we're not just going to let T1 occupy the processor. What we're going to do is we're going to switch the processor, or the core rather, to running a different thread. Okay, let's say T2. Now let's say T2 also starts a memory operation, right? So actually, I'm going to pair these up. Okay, so let's say T2 also starts a memory operation over here. Okay. Now, this would also take a long time to finish. Maybe it finishes at this time point. Okay, so instead of waiting for T1 and T2's memory operation to finish, we're now going to switch the core to running a third thread. Okay, so let's say it also starts a memory operation, which starts and finishes at these two locations. Okay, and again, so we keep switching. So as long as you have a thread that has started a memory operation, but it's waiting, and the memory operation has not completed yet, then we're going to keep switching to new threads. Okay, so maybe here you start a fourth thread. Okay. Now, at the end of this, now eventually T1's memory operation is going to finish, right? So for example, at this fifth time point over here, right, T1's memory operation has now finished. Okay, so now we no longer need to switch to a different thread. Okay, we can, so now instead of switching to a fifth thread, we're going to go back to T1. Okay, so then if you go back to T1, then maybe T1 now it has the result from its first memory operation, and so now maybe it decides to do a second memory operation. Okay, so the second memory operation, it starts over here, and again it's going to take many cycles to finish. But now again, instead of waiting for T1's just waiting for T1, right, we're going to switch to T2. Okay, now T2, you notice that at this time point, its first memory operation has finished. Okay, so now we can switch to T2, and T2 is going to do some computation based on the data that it got back, and then maybe T2 is now going to decide to do yet another memory operation. Okay, so now we're going to switch away from T2 to T3. Okay, T3 by this time point has finished its first memory operation, so then now it can do its computation. Okay, so basically the way this works is that we keep, whenever a thread does a high latency memory operation, we're not just going to wait for that thread to finish, we're going to switch the core to processing a different thread. So this is why it's called massive multi-threading, okay? Because we're going to have a large number of threads that we want to switch between. Okay, now we do need to, now one thing is that we have to ensure we have lots of threads to switch between. Okay, because imagine that we only had, let's say, 2 threads to switch between. Okay, so sorry, let me change to a different color here. So let's go for blue. Okay, so now imagine that we didn't have these two threads down here. Okay, so we just have T1 and T2. Okay, if you just have T1 and T2, then T1's memory operation starts here and ends here. Okay, so then since T1's waiting, we're going to switch to T2, right? Which is going to start and end over here. But now T1 and T2 are both waiting, and now at this third time point, right, if we only have 2 threads, then we have nobody else that we can switch to. Okay, so then we just would have to wait for these two cycles where nothing's happening until T1's memory operation finishes, right? So so therefore, in order to implement this massive multi-threading, we actually need to make sure that we have lots of threads that we can keep switching to. Okay, we need more threads. Okay, and also we need to make sure that when we switch from one thread to another, we can do it very quickly. Okay, because here, if the switching time from let's say T1 to T2 is very slow, right, then we don't get as much. Okay, so we need 2 things. We need to make sure the thread switches are fast, and we need to have many threads to switch to. Okay. Yeah, but if we satisfy both conditions, right, then you can see that what will be happening is that we'll actually be getting results back from the memory very quickly, right? So even though the overall latency of one memory operation is high, but because we're pipelining many operations together, right, then effectively our actual memory throughput is high. Okay, so now we said that we need to switch between these threads, right? So how do we switch between the threads? Well, each SM has its own scheduler, okay, to do the thread switching. And by the way, this is different from the thread scheduler that allocates blocks of threads to the SMs. Okay, so that thing was called the gigathread scheduler. And here, this is different. So there's one gigathread scheduler for the entire GPU, whereas here, every SM has its own scheduler. Okay, now what does it take to switch a thread, right? Because we want to switch threads quickly. How do we ensure that the threads can switch quickly? So I talked about this last time, so let me just briefly repeat it, okay? So what happens is we saw that each SM actually has a large number of registers, okay? So let's sort of draw a bunch of registers over here, okay? So let's say that there are 64,000 registers, okay? Now what we want to do is we want to, and so these 64,000 registers are, let's say, divided between 1,000 threads. Okay, so then basically each thread has 64 registers. Okay, now we're going to group these threads into these things called warps. Okay, so I'll talk more about this later. But basically a warp, right, is going to have something like 32 threads in it. Okay, so we're going to have many warps. Okay, in fact, if you have 1,000 threads, we're going to end up with like 32 warps. Okay, oops, warp, singular. All right. So now the SM scheduler, okay, is going to keep switching between warps, okay, and these warps have been pre-allocated their registers. So this is something we said last time, which is that when this block of 1,000 threads was allocated to this SM, right, all of the registers that this block needs were pre-allocated to the block, okay. So all of these warps have their own dedicated registers. Okay, so therefore, in order to switch between the registers of two different warps, right, you don't need to do any reading or writing. All you need to say is that instead of looking at this block of registers, right, I'm going to switch a pointer and say that, well, let's go look somewhere else. Okay, let's go look over here at the next block of registers. Okay, so switching between warps of threads just involves like sort of changing the value of a pointer to look at a different set of registers. And once you have this new set of registers, right, then these registers over here, right, they define all of the state needed to run this warp. Okay, and so now we can start executing the next warp. And so this is this first of all incurs very little overhead, because all you need to do is switch this one pointer from different chunks of registers, right? And also this points to why GPUs have to have so many registers. Okay, it's because we need to do this pre-allocation of the registers to the threads, right? If we had fewer registers, then each time we switch between the threads, we might need to read or write the register values from memory, from main memory, global memory, and that would take just way too much time. Okay, so we can't afford to do that. So we have to just keep all of the register values in the big register file. Okay, now also, how do we decide which threads or which warps to switch to? Okay, well, this is being, so for example, eventually we said that T1's memory operation is going to finish at this time point. Okay, so when it finishes at that time point, right, we don't want to switch to a new thread anymore. We want to switch back to T1, right? So how do we know that we should be switching back to T1? Okay, so this is because this SM scheduler has this thing called a scoreboard, okay, which keeps track of which threads are doing memory operations or doing other types of blocking operations. And when this blocking operation has finished, right, like when the memory request has returned, right, then the SM scheduler can switch to back to the thread. Okay, and again, this is only effective when we have many threads to switch between. Okay, so so if again, if you don't have enough threads, right, then this whole thing is not going to work, because we're going to have to be waiting for a large chunk of time. Okay, and so this is why now each SM only has something like 32 cores, let's say, okay, 32 or 64, something like that. Okay, so let's just say 32 cores. Okay, however, we saw that SMs usually you want to schedule several hundred or maybe even 1,000 threads onto this SM. Okay, so this is because if you schedule 1,000 threads onto this SM, then you can run, if you have 32 cores, you're going to run chunks of 32 threads at a time. Okay, and once this chunk, once one chunk of 32 threads blocks on a memory operation, you can switch to the next chunk of 32 threads. So we need many chunks of 32 threads, right? These chunks are the warps, right? We need many of these warps to switch between. Okay, so we need, so if we have 1,000 threads, then we can have up to 32 warps that we can be switching between, right? So this helps us do our massive multi-threading. And this is also the reason why you want to maximize occupancy on an SM. Okay, so remember from the previous lecture that we talked about, our goal in deciding things like block size or other parameters is to make sure that we can run as many threads as possible on an SM. Okay, so why do we need to do that? Well, it's because we want to be able to achieve this massive multi-threading, okay, which is used to hide the latency of the global memory. Okay, yeah, so we need a high occupancy. Okay, so now we've talked about the latency issue, okay? And the way to address high latency is to do this thing called latency hiding using massive multithreading, okay? However, that's not enough, okay? Because in addition to having a latency bottleneck, we also have a bottleneck in terms of global memory bandwidth, okay? Now, remember that latency and bandwidth are not the same thing, right? You could have very low latency, but if you have tiny bandwidth, you're still going to get very poor performance. Okay. So now we need to address the fact that the global memory has limited bandwidth. Yeah. Okay. So just to give you an idea how severe this problem is, right? So suppose you have a GPU which has a performance of 1.5 teraflops. Okay. So every second it'll do 1.5 trillion operations. Right. So that's fairly decent. Okay, now suppose this GPU has a memory bandwidth of 200 gigabytes. Okay, now remember, now suppose you're doing something like a matrix multiplication process. Okay, so then there we have this partial sum that we were computing, right? So if you look at the so this computation, it's going to do some computations, right? For example, this addition assignment, right? But it's also going to do some memory operation. For example, it's going to read from this this matrix, right? M and then N. Okay. So in total, if you count this up, right, we are doing a total of what is it? We're doing a total of 1, 2, 3, 4, 5, 6 floating point operations, right? And to do that, we need to do 2 memory operations, right? We need to read from M and read from N. And these things are stored in global memory, right? Because these matrices are too large to store in like shared memory. So therefore, the ratio of computation to memory operations, right? So there's actually a name for this. It's like the compute to global memory access ratio is 3 to 1. Okay, now if you have 200 gigabytes per second of bandwidth, okay, so each floating point value is going to cost you 4 bytes. So we're only going to be able to read 50 billion floating point values per second. Okay, and for each floating point value you read, right, you're going to do 3 computations. So therefore, you can only do 150 billion computations per second because of your memory bandwidth. Okay, and this is only 1/10 of what we can potentially achieve, which is like 1.5 trillion. Okay, so here we're very limited by the memory bandwidth. Okay, so so now to solve this issue of memory limited memory bandwidth, okay, we're gonna use this method called data reuse. Okay, so basically we're going to try to minimize the amount of data that we have to read from global memory. Okay, so the way, so I'm going to illustrate this with an example of matrix multiplication again. Okay, so suppose we're doing matrix multiplication, and suppose you have a block of threads over here, this yellow block P. Okay, and let's say the dimensions of this are tile width by tile width. Okay, so we have we have tile width squared number of threads within this thread block. Okay, now if you do matrix multiplication in the naive way, okay, which is what I'm showing you above, then what happens is if you look at a thread in this thread block, okay, so then this thread, in order to compute its value, it's going to have to read a bunch of values from M, right? It's going to have to read these values. Actually, it's got to read more values than that. It has to also read the rest of this row, okay? But at least it has to read, the first part of this row, okay? And it also has to read the first part of this column. Okay, so all of those, if we just store M and N in global memory, each of those reads is going to be global memory accesses. Okay, so in fact, if the tile here is going to be tile width by tile width, right, then P here is doing tile width global memory accesses for M, and then another tile width global memory accesses for N. Okay, so P itself is reading 2 times tile width amount of data from global memory. Okay, and now in total, you have a tile width times tile width, so tile width squared number of threads, right? So in total, so each of them does this many global memory accesses. So in total, we're doing 2 times tile width cubed number of global memory accesses. Okay, so that's going to hurt our performance a lot. Okay, now the thing about data reuse, so the property that we're going to exploit is the fact that if you look at 2 different threads, okay, so let's look at 2 threads on the same row, okay. Now, so this thread is going to be reading all of this data from M, right? But if you look at another thread from the same row, then it also needs this data from M, right? It needs the same block of data from M, okay. So, so if we have these 2 threads operating independently, then the first thread is going to read this chunk of M, right? And the next thread is going to reread this chunk of M from global memory. Okay, so we're wasting a lot of, so we're doing a lot of redundant accesses to global memory. Okay, because these guys are duplicating their work. Okay, and in fact, all of the threads, right, on this row, they all need to read this part of the global memory. Okay. So if they all operated independently, right, they would all be reading the same data over and over. Okay. Now the same applies to columns. Okay. So this thread needs to read this column of data from N, right? But this thread also, if it's on the same column, it also needs to read this data, right? And so does all the threads on this column. Okay. And if all those threads operated independently, they would again be wasting a lot of accesses to global memory, right? Because they'd be reading the same thing over and over. Okay, so therefore the observation is that the data in the purple blocks, okay, so this little block of M and little block of N, okay, this can be reused. And what that means is if somehow we can load this data from this purple data from M and N, if we can load it from global memory just once, okay, and then we can share that data between all of the threads in this yellow P tile. Okay, yeah, and if we can do that, then what happens is how much global memory accesses do we need to make? Well, then it's just tile width squared, right? That's the size of this purple tile, right? And the same thing for the tile for N, right? So in that case, it's going to be 2 times tile width squared number of global memory accesses that we need to make for these 2 tiles, right? And then we can compare that to previously we needed to make 2 times tile width cubed number of global memory accesses. Okay. So the idea is somehow we want to have all of these threads not load the data from M and N independently, because then they'd be doing redundant work. We want them to cooperate with each other and load this data just once. Okay, so then the way we're going to do this is that, remember, we have these little chunks of memory called the shared memory, right? So we have, let's say, 64 kilobytes of shared memory. Okay, so what we're going to do is we're going to take this little chunk of data from M and N, right? And we're going to load it once from the global memory to the shared memory. Okay, just once. Okay, so that's going to cost us 2 times tau width squared number of accesses to load it from global memory to shared memory. And then once it's in shared memory, then we can have all of these the threads in p tile access this chunk of shared memory. Okay, right, and because shared memory has such is going to be so much faster than global memory, then and also have much more bandwidth, right? Then we're going to get a big boost in performance by doing this. Okay, so so the actual way this is going to work is that, well then, you might be saying, okay, well, why not just load all of M and N into from global memory into shared memory? Just do it once, and then you're done. Okay. Well, the reason is that the shared memory is small, right? So we can't afford to load all of M and N into the shared memory. We can only load little parts of it at a time. Okay. So then, what I'm showing over here are the parts of M that we're loading each time. Okay, so for example, in order for this thread to do its computation, right, it actually needs to read this entire row and multiply by this entire column over here. Okay, but we can't afford to store all of this purple data and from M and N in the shared memory at the same time. We can only afford to store these 2 squares labeled 1 at a time. Okay, so then what's going to happen is our computation is going to proceed in phases. Okay, in the first phase, we're going to be loading this 1 tile from M and N. Okay, so we're just going to load the 1 tile, and then we're going to load it from global memory into shared memory, and the threads are going to do some computation on this 1 tile. So basically, they're going to read maybe this data times dot product of that data, and then they're going to get sort of a partial value for what this should be. Right? Okay, so then after that, now we're going to go on to the second phase. And we're going to load this second block of data from M and N. Okay, so that allows them to get maybe the next part of this row and the next part of this column. Okay, so that allows them to get more to compute more of this partial value over here. Okay, so now we can afford to store both this square from M and N in the shared memory at the same time if we make these tiles small enough. Okay. And then in the third phase, we're going to evict the data from the second phase. We're going to take it out of the shared memory, and now we're going to load the data from the third tile into the shared memory. Okay, and that allows them to compute this part of the dot product. And now this thread has computed the entire value. Okay, because he's computed the dot product over here, he's done it over here. Right, and he's got the third part, so now he's got the entire value for himself. Okay, and at any time point, all we needed to do was we only needed to keep 2 of these purple tiles, 2 of these purple squares, okay, in shared memory at a time. So if we make these tiles small enough, then they're going to fit just fine in the shared memory. Okay, yeah. So this just says what I was describing. So the number of phases that we have, okay, is whatever this width of the matrix is, right, divided by the tile width, right? Okay, and yeah, and in phase I, right, the threads in this p tile, this yellow tile here, right, they're going to cooperate in loading the data from the ith tile, right, from the global memory into the shared memory. Okay. And then, in order to access this data, right? So this guy needs this data and this data. Well, now these 2 things are now sitting in shared memory. Okay, so this thread can access that data very quickly. Okay, and then after all of the threads have finished using all the data from these 2 tiles, right? Then we can go on to the next tile, the next phase. Okay. All right, so this is a summary of how this process goes. Okay, so so now the only thing we haven't talked about is how do we have the threads cooperate in loading these purple tiles. Okay, well that's easy because here we have a bunch of threads like this, right? And in order for them to and so on, right? In order for them to load this purple tile, we just have one element. We have, for example, this element, right? He's going to load this part, right? The second guy, this guy, he's going to load that data from this purple part of M, right? So we just assign each thread to load one element of M from global memory into shared memory. Okay. Likewise, we're going to have these guys load the corresponding elements from N. Okay. So each thread over here is processing one p-value, and that thread is going to load the corresponding value from N from global memory into shared memory. Okay. All right. So then let's look at the code for doing this. So the code for doing this is, first of all, we need to allocate some shared memory in order to store these purple tiles, right? So that's being done over here. Okay, so notice that we have to prefix this with _shared, right, to indicate that it's shared memory. And the size of the shared memory is going to be tile width by tile width. Okay. All right. So next, we have, so the threads are going to have, so they have their block ID and their thread ID. Okay. Now, we did these calculations in the last class. So in order to calculate which row, right? So here, each thread is going to process a row, right, and a column, right? And to calculate that, we're going to do this calculation over here. Okay. And now, the thread over here, right? So it's basically, so this thing over here is tx. Okay. Sorry, let me write this like that. Okay. So this is tx over here, okay, and then this is ty over here, okay. So this thread is located at where is it? At tx and ty over here, okay, within this thread block, okay. So therefore, this thread is responsible for loading the corresponding element from M and N. Okay. So what we see here is that we're going to load this element from the, so D here stands for device memory, which is the global memory, okay? So we're going to load it from the correct position in the global memory, right? So you can sort of work out this computation itself, but it's basically where is this item located in M, okay? And then we're going to load it into index tytx in the shared memory, okay? In this, so the shared memory is indicated by this little s over here, okay? And we do the same thing for N. Okay, we load it from the global memory into the shared memory. Okay. Now we need to make sure that all of the threads have finished loading all of this M block and this M block, right, before we do any computations, right? Because otherwise, each thread is just loading one piece of data, right? So if if this thread it's loading, it's loading two pieces of data, okay? If it just goes on after it loads these two pieces of data, right? Now this thread needs to actually compute this row dot product this column, right? But what if, and this column, for example, this value over here, right? Who's loading that value? Well, it's going to be this guy, right? Now, what if this guy hasn't finished loading this value yet, right? Then the thread over here cannot do its computation. Okay, so this thread over here needs to make sure that this other thread has finished loading this piece of data. Okay, now how do we do that? Well, we need the threads in this thread block to synchronize with each other. Okay, we need them to all perform this data load operation. Okay, so we're going to use a barrier. Okay, so the barrier is going to say that all the threads which have finished their loading their two pieces of data, they're going to wait here until every thread has finished loading its piece of data. Okay, when every thread is finished, then we have this entire purple block of M and N being loaded. And now we can go ahead and do our computation. Okay, but we need to wait until this entire thread gets loaded. Entire tile gets loaded. Okay, yeah, so that's, so in order to do the synchronization, this is called sync threads. Okay, so sync threads lets all of the threads in a thread block, it creates a barrier for all the threads in a thread block. Okay, so this is basically a barrier. Okay, so next, we're going to do the actual computation. Okay, so now we've got the data from these purple blocks loaded into shared memory. Okay, so now we can do the accesses from shared memory. We can do the computation from shared memory. Okay, so now, yeah, so this is the calculation. You can check that this code works correctly. And then so this is going to basically each thread is going to read from its respective row and column from shared memory, right, and multiply and dot product them, okay, and then add that into this p-value thing. And now we want to make sure that all the threads have finished their computation before we go on to the next phase, okay, because what is the next phase? The next phase is to like throw out all of this data and then load the next chunk of data, okay, right? So we don't want to throw out this data until all the threads in this thread block are finished using this these chunks of data, right? So in order to know that all of the threads have finished using this chunk of data, we're going to put another barrier over here, right? Another sync threads, which is to say that all of the threads have to are going to wait here, are going to wait at the barrier until they've all finished their computation. Okay. And then when that happens, right, then we are going to go on to the next iteration of the for loop. Okay, and the total number of iterations we have, right, is the number of stages that we have, right. We said that, you know, here we have, like, let's say 3 stages, and this is equal to the width divided by the tile width. Okay, so the width divided by the tile width. Okay. And in the end, this guy P here, right, he's going to end up with the correct value for this entire row times this entire column. Okay, and then we can write that result back to the global memory. Okay, so now, by the way, this value here, this is being let's see. So should I talk about this now? Okay, so I'll mention this again later, but these values here, okay, so this is stored in registers, okay, so the way you know it's a register, it's being stored in registers is because, you know, variables that you declare as automatic variables, okay, they are by default stored in registers. So these things here are also stored in registers, okay, so yeah, these BX, all this stuff is stored in registers, okay, this stuff, right, because we prefix it with shared, this is being stored in the shared memory. Okay, and then this stuff here, right? This is memory that was allocated by the CPU, and that's global memory. Okay, so that is the this tiled matrix multiplication algorithm, right? It's tiled because, you know, we read from these tiles. Okay, and this algorithm, because it's making use of the shared memory, right, this can actually achieve much better performance than the naive algorithm, right? So the naive algorithm was just, where is it? It's just this algorithm over here, where every thread independently reads part of the row and column. Okay, so let's see how much better performance we can get. Okay, so so suppose we have a m by m matrix. Okay, and suppose that we broke it into tiles of size m by m. Okay. Now, we said that the naive algorithm, right, it's gonna, we're gonna produce n squared elements of output, right? And then each, so we have like n by m matrix over here, right? We have this output matrix over here, right? We have the other matrix, right? So this is m by n, right? So each guy over here, right? So we have n squared of these guys, and each guy needs to read n values from m and n from n, n values from n, capital N. Okay, so that is going to be 2n global memory accesses, right? If we use the naive algorithm, 2n global memory accesses for each element of output. So that comes out to 2n cubed global memory accesses. Now, if we look at the shared memory algorithm, okay, so the shared memory algorithm is going to break the stuff into these blocks, right? Into these blocks, okay. And the number of blocks is if you have an m by m matrix and the blocks are size m, right? Sorry, this is kind of hard to write over here. Okay, then we're going to have n divided by m squared number of blocks. Okay, and each block does n divided by m phases, right? So for example, you know, these are the phases for this guy, right? 1, 2, 3 over here. Okay, so how many phases are there? It's n divided by m. Okay, now in each phase, how many global memory access do we do? Okay, so for example, in this phase, right, we have, so this is a m by m block, right? This is, well, it's too small to write over here, but this is this block over here, right? This is an m, this is an m by M block. Okay, so so we're going to read all of this data from global memory into shared memory once. Okay, and we do this once for the M matrix and another time for the N matrix. So therefore, it's going to be 2M squared number of reads from global memory into shared memory. And this is per phase. Okay, and the total number of phases is N divided by M. Okay, and in each phase, you do that number of global memory accesses, right? And this is just for one block, right? This is for this thread block. Okay, now in total, you have this number of thread blocks, right? So if in total, if you look at how many thread blocks are, it's going to be that many. Okay, so then you multiply everything together, and you get that the total number of global memory accesses by the shared memory algorithm is 2n cubed divided by m. Okay, so now we compare this, let me erase this, we compare that to the total for the naive algorithm, and you see that we're doing a factor of m less global memory accesses. Okay, all right, so okay, so first of all, you might be saying, okay, why not make m as large as possible, right? Because if you make m really large, then you're gonna go much faster. Okay, well the problem is that you have to be storing these tiles in the shared memory, right? So your shared memory is pretty small. So you can't afford to make these tiles arbitrarily large. There's like an upper bound on how large you can make them. Okay. Okay, now I want to mention that this doesn't, so we've reduced the number of global memory accesses, okay? But we don't really reduce the number of total memory accesses because after you've read these little m by m tiles from global memory to shared memory, right, then these thread blocks, right, so remember we have these thread blocks, right, then this guy needs to read from shared memory. Okay, and if you count up the total number of accesses by this thread block from shared memory, actually from all the blocks, if you count up their accesses from shared memory, it is still going to come out to 2n cubed. Okay, so we're not reducing the total number of memory accesses, but we are decreasing the number of slow accesses from global memory, and we're increasing the number of fast accesses from shared memory. Okay. And yeah, and because shared memory is both faster and has more memory bandwidth, then we get much better performance. Okay, so let's actually look at how much improvement in performance we can get. Okay, so we said that if we use m by m tiles, we reduce the number of memory accesses by a factor of m. Okay, so consider using 16 by 16 tiles, then we reduce global memory usage by a factor of 16. So now, previously we were getting something like, well, we could read 50 billion numbers, okay, from global memory, right? And we do 3 flops per byte that we read. But now, since we can effectively increase our bandwidth by a factor of 16, now we can end up doing 2,400 gigaflops, okay? Compared to if we didn't have the shared memory algorithm, we could only do 150 gigaflops. Okay, so we've increased our performance by a factor of 16. Okay, and if we're using tiles of this size, then let's check that this does indeed fit in shared memory, right? So we have 16 by 16 tiles, 4 bytes each value, right? And then we need to store 1 tile from M and from N, right? So that just comes out to 2 kilobytes of shared memory. Okay, that's not a problem. We have 48 kilobytes of shared memory. Okay, so yeah, so even if you have, let's say, only 16 kilobytes of shared memory, right? So let's say we configure it to have 48 kilobytes of L1 cache and 16K of shared memory. For using 2K per block, right? We can still run 8 blocks per SM, okay? And that can fully occupy an SM. Okay, now sometimes you don't want to use like very large tiles. One is that it might not fit in shared memory, and even if it fits in shared memory, you could have run into problems like this. So, for example, if you use 32 by 32 tiles, right, then you have 1,024 threads per tile, right? And so, if you can only run 1,500 threads per SM, then you can only run you can't afford to run 2 blocks, so you can only run 1 block with 1,000 threads, so you only get 2/3 occupancy. Okay, so in fact, in this case, we see that you don't want to use a larger tile because you get lower occupancy. Okay, and using a 16 by 16 tile is already enough to saturate your performance. So there's no need to go to larger larger tiles. Okay, so now this basically this use of shared memory that we saw, okay, which is a way of like effectively increasing your memory bandwidth. Okay, so this is very useful in practice, right? It's actually the same principle as caches, okay, because you're reusing data, right? So here we read those purple tiles and we reuse that data from shared memory instead of from the cache. Okay, so this is a form of temporal locality, and it's a very important technique. It's not easy to use necessarily because we know that the shared memory is really small compared to global memory, right? However, if you can somehow redesign your algorithm to make good use of this shared memory or cache, right, then you can get a big boost in performance. Okay, so now let's just look a little bit at how we can declare these different types of memory, right? So, so the way that you declare a register is that, again, unless you make a special declaration, then by default, the variables you declare are going to be stored in the registers. Okay, so so for the registers, they can only be seen by the thread that created, that declared this this variable, right? So the scope is for a thread, right? And this the lifetime of the data is when the thread terminates, then the data goes away. Okay. For the shared memory, right? The way you declare it is with this double underscore shared, and this is visible to the entire block of threads. Okay, so if a thread block declares, if one thread from the thread block declares some piece of shared memory, right, then all the other threads from the thread block can see that. Okay, and the lifetime is for the block's lifetime. Okay, and then you have this global memory, right? If you declare memory as being device like this, right, then it's going to be global memory. Global memory is visible to all threads in your entire grid of threads. Okay, and the global memory stays around for the entire application. Right, and the same for the constant memory, which we didn't talk much about, but it's the same. Okay, so then, yeah, so notice that automatic variables, right, declared without any qualifier are in registers. Okay, the exception is arrays that threads declare. Okay, so if a thread declares a large array, right, then maybe that doesn't fit very well in the register, right? So in that case, those arrays are going to be stored instead in the global memory. So that'll be much, much slower. So when you have threads declaring arrays, you got to be careful and keep in mind where that's being stored. Okay, so now let's talk about synchronization. Okay, so synchronization. So we talked a bit about synchronization last time. So what we said was you could not synchronize between two different blocks. Okay, but now here in the tiled matrix multiplication algorithm, we saw that there is a way to synchronize within a single block. Okay, so and you need this sometimes because, for example, in the matrix multiplication algorithm, right, we need to make sure that we finish loading the m and n tiles into the shared memory before we do any computations, right? Because otherwise, if you start the computation too early, maybe the value is not in the shared memory yet, and so you would compute the wrong value. And we saw that the way to synchronize within a block is to use this barrier synchronization, which is sync threads. Okay, so the scheduler for the SM will make sure that all the threads in the block are going to do the barrier at where the sync threads occurs. Okay, now there are a few things that you need to be careful about when you use sync threads. So for example, if you have a bunch of threads that in a block, right, and then if they do a sync threads, but suppose one of the threads for some reason goes into like an infinite loop. Okay, so you had some bug in your code, so one thread goes into an infinite loop. Okay, what's going to happen is the other threads in that block are going to be waiting for this looping thread, and so they would be blocked forever. Okay, so so even though you only have one thread in an infinite loop, all of the other threads would also be blocked at the barrier. Okay, the other thing is that suppose you have a branching statement in your code. Okay, then if you have a barrier in one branch, right, but then if you have some threads that go through the other branch without the barrier, okay, then again, you're going to have the threads are going to block forever, okay, because you have like part of the threads are blocking at the barrier in one branch, and the other threads have gone into the other branch without the barrier, okay? So you'll never have all the threads reaching the barrier, so therefore all the threads will be blocked. Okay, so then so you have to make sure that the sync threads occurs in both branches, okay? And then you have to make sure that all the threads will go through the same branch. And the final thing about sync threads is that it can sometimes cause wasted work. Okay, so for example, if you have a sync threads over here, right, then the thread that and if some threads are slower than other threads, then one thread might reach the sync threads much earlier than other threads, and so that fast thread would be waiting for the slow threads. Okay, so he'll just be wasting his time. Okay. And we said that one way you can deal with this is if you have if you have smaller thread blocks, then you have less chance of this happening. Okay, but we know that you don't want to have very small thread blocks because that's going to hurt issues like latency hiding and yeah. Okay, so the upshot is that since sync threads has these causes these types of problems, then you want to sort of avoid them as much as possible, right? Of course, sometimes you have to have these sync threads, but you don't want to just put them in arbitrary places unless you really need to. Right, and this one just sort of repeats what I was mentioning last time, which is that different thread blocks cannot synchronize with each other. Okay, so you cannot depend on the fact that block 2 over here is going to run after block 0. Okay, because if you run on a different architecture, you could very well have blocks 0 and 2 running concurrently on different SMs. Okay, so now we're going to move on to the second part of this, which is warps. Okay, so warps are this. So basically, so warps. So the reason warps come about is because in an SM we have some number of cores. Let's say we have 32 cores. Okay, so now the goal. So what the SM hopes will happen is that all 32 of these cores will run the same instruction. Okay, if they run the same instruction, then then it's operating in a SIMD fashion, right? Single instruction, multiple data fashion. Okay. Yeah, so in fact, the degree of SIMD-ness, okay, like how large your SIMD unit is, right? How many threads, how many cores are running the same operation, that determines the size of a warp, okay? And that's usually 32 threads in current generations of GPUs. Okay, so then a thread block is actually divided into multiple warps, okay? Each warp has a bunch of consecutive thread ID values. Okay, so for example, first warp has IDs 0 to 31, right? Second warp has 32 to 63, and so on. Okay, now the goal, what the GPU hopes to have happen is that your entire warp does somehow the same thing. Okay, so now that same thing, it can actually mean, so there are different, that means different things. Okay, so I'm not saying that right. You want, because a warp is supposed to represent a SIMD unit. Okay, you want somehow all the warps to have the same behavior in some sense. Okay, so I'll show you exactly in what sense you want them to behave the same way later. Okay, there are several. In fact, there are several senses in which we could understand that statement. Okay, now it is allowed for. So first of all, different warps can do different things. Okay, because the SIMD unit is simply one warp, right? Then if you have two different warps, they're not in the same SIMD unit, so it's fine if they do different things. You don't get any performance loss. Okay, but if you have threads within one warp doing different things, then you will have a SIMD loss. Performance loss. Okay, so what do we mean by doing the same thing? Well, there are several issues. Okay, so the first one is called coalesced memory accesses. So we want the entire warp to make coalesced memory accesses. Okay. Also, we want the warp to avoid flow divergence. Okay, and also we want the warp to avoid bank conflicts. Okay, so these are the senses. So this is what we mean when we say that the thread should do the same thing. Okay, we want them to do coalesce memory accesses, right? We don't want them to diverge, and we don't want them to have bank conflicts. Okay, so now let me talk about what these things are, right? What is coalesce memory accesses and divergence and so on. Okay, so first of all, memory coalescing. Okay, now the way the GPU memory works is that the global memory. Okay, so this only applies to global memory. So the global memory is actually divided into segments, okay, which are kind of like cache lines. But anyways, these segments are, let's say, 128 bytes large. Okay, so that's 32 floating point values. Okay, now suppose an SM, right? So an SM, let's say, has 32 cores, and these 32 cores are doing a warp of 32 threads, right? So one thread per core. Okay, so this SM is doing a warp of 32 threads, and they're all executing a SIMD instruction, right? And let's say that this instruction is to read from global memory. Okay, now let's look at where these threads are reading. Okay, now if it happens that the threads are all reading, so the global memory is divided into these segments of 32 values, right? Now if all the if this entire warp of threads is reading from the same segment, okay, then the GPU hardware can actually detect this, and it's only going to transfer data from the single segment from the global memory to the streaming multiprocessor. Okay, and in that case, since we're only transferring one segment, right, this is called a coalesced memory access. However, if we have a situation where the threads in a warp, right, if they're accessing global memory locations from different segments, okay, so here we're looking at 3 different segments, right, the data resides in 3 different segments, okay, then, in fact, the GPU hardware is going to transfer all of the first segments. Okay, so even though we just want, these 2 pieces of data, the GPU is actually going to transfer the entire segment. Okay, so it's going to transfer data that we don't even need, but that's how the hardware works. Okay, it's also going to transfer data from the segment. Okay, so as long as a thread accesses any data from the segment, the GPU is going to transfer this entire segment, including data we don't need. Okay, and it's going to transfer a 3rd segment, right? So we only need this one, but we get all this other stuff we don't need. Okay, so in fact, if the locations that's being accessed by this warp, if they're in k different segments, then in total, we're going to be, the GPU hardware is going to transfer all k segments, and so that's going to be k times 128 bytes, because each segment is 128 bytes. So in that case, we say that the access is uncoalesced. Okay, and in fact, in the worst case, since you have 32 threads, right, they could each be accessing a completely different segment. So in that case, you're going to end up transferring 32 times 128 bytes is 4 kilobytes. Okay, just to read 32 floating point values, you're transferring 4 kilobytes from global memory to the SMs. Okay, so this is eating up a huge chunk of your global memory bandwidth. Right, we have very limited global memory bandwidth, and now we're wasting it in a big way. Okay. So the idea is that we definitely do not want these uncoalesced memory accesses. Okay, we don't want this situation where you read multiple segments. We want this situation where you only read from one segment. Okay, so we want to make global memory accesses as coalesced as possible. Okay, so let's do a concrete example of this. Okay, so suppose you have a matrix over here, right? So remember that matrices are stored in row major format. And so, so then this is how the matrix is actually laid out in the data, in the global memory, okay? Now, suppose for this example that our global memory, so it's got segments, and suppose now our segments are 4 elements wide, okay? Instead of 32 elements, okay? So that means that we can transfer 4 consecutive elements in one step, okay? And now suppose our warps also have 4 threads each, okay? Now, suppose you want the warps to iterate through this matrix, either row by row or column by column. Okay. Now let's first look at it row by row. Okay. If we iterate through this row by row, then we first want to access this entire red row. Right. Now, how is the red row stored in global memory? Well, all of this red row is stored consecutively in global memory. right? Because that's how the row major format works. Okay, so in the first the first time we run this warp, right, we're reading these red memory locations, and since they're all consecutive and they all lie in the same segment, then this is a coalesced memory access. Okay, on the next iteration of this warp, we're going to read these blue values over here. Okay, the blue values are also consecutive in global memory, right? So they're within one memory segment. So it's we do another coalesced memory access. Okay, and then we read these green values, which we get a coalesced memory access, and then the yellows are also coalesced. Okay, so in total, we've done 4 coalesced memory accesses. Okay, so now let's change this so that we access this matrix column by column. Okay, so column by column, the first iteration of these 4 threads, okay, we need to read these locations, right? We need to read a red location, a blue one, a green one, and this yellow one. Okay, now where are these locations stored? They're stored, so the first red location is over here, right? The first blue location, right? This is over here, right? The green one is over here, and the yellow one is over here. Okay, now these 4 memory locations that this warp of thread is reading, right? They lie in 4 different memory segments, right? Each color here is a memory segment. Okay, so they lie in 4 completely different memory segments. Okay, so we have a completely non-coalesced memory access on the first iteration. Okay, now what about the second iteration? Second iteration, they're going to read, so this value, this value, this value, and that value. Okay, so these values are lying at these locations. Okay, and again, these are non-coalesced. Right. In the third iteration, we read this third column, and again, so that's going to be, at these locations marked by 3, and they're again non-coalesced. So when we read column by column, then we get completely non-coalesced memory accesses. Right. When you read row by row, right, everything was perfectly coalesced. Right. First iteration, you read this segment, and then second iteration, that segment, and so on. Okay. Whereas once you read column by column, it's completely non-coalesced. Okay, so then now what do you do? Okay, because sometimes you might want to read this matrix column by column. Okay, so we're gonna try to improve coalescing, and the way we're gonna do this is we're gonna make use of the shared memory again. Okay, so suppose that so if we want to so ultimately we want to read this matrix column by column. Okay, like in this situation over here. Okay. But in order to do this, what we're going to do is we're going to copy, so this matrix, right, initially it was sitting in global memory. Now we're going to copy it over into shared memory. And when you copy into shared memory, you don't have to read this matrix column by column. You can read it row by row, right? Nobody requires you to read this column, when you're doing the copying, nobody's requiring you to do this column by column. So we're going to do it row by row. And if you do it row by row, then we saw that you can do this in a perfectly coalesced fashion. Okay, so this copy here is coalesced. Okay, and then once you've got it into shared memory, now you can read it column by column. Okay, so shared memory does not have this issue about memory coalescing. Okay, memory coalescing is only an issue for global memory. So therefore, we get it into shared memory, and now we read it column by column, and we don't have any performance penalty. Okay. Yeah. So okay. So that's our example for memory coalescing. So next, let me talk about warp divergence. Okay. So warp divergence basically means that so our streaming multiprocessor is supposed to be a SIMD processor. Okay. So it's got, let's say, 32 processors, or 32 cores rather, and the cores are supposed to do the same thing. Okay. So it's efficient when all the cores do the same instruction. Right, like they're all reading or they're all adding or something. Okay, so if they all do the same instruction, then we can actually, the SM can run the entire warp in one pass. Okay, because we have 32 cores and we have 32 threads, so we so in just one sort of iteration, we can complete all 32 operations for the warp. However, if the code has branches, okay, then the threads might run different instructions. Okay, so for example, some threads might be doing an add, and some might be doing a subtract. Okay, or yeah, let's see. In this example, we have 3 branches. Okay, some threads are going to be doing an add over here, right? So the ones which are divisible by 3, they're going to be doing an add, right? The ones which are 1 modulo 3, they're going to be subtracting, and then the other threads are going to be multiplying. Okay, so now the warp of threads are trying to do 3 different instructions, and because of the GPU architecture, they cannot do all 3 instructions in the same cycle, in the same iteration. Okay, so in fact, we have to break these threads into 3 different cycles because they're doing 3 different operations. Okay, so this is called warp divergence, right? The threads are doing different things. Okay, so in fact, if your threads have, within the warp, have k branches, okay, so if they're doing k different things, okay, then the SM can actually take k passes to run the entire warp. Because basically in each pass, it's going to do only the operations from one branch. Okay, so for example, in the first pass, it's going to take all of the threads which are, so let's say we have threads which are 0, 1, 2, 3, 4, 5, 6, right? Let's just do a few more, right? 8, okay, right? So these guys, right? They're doing the adds, right? And then these guys are doing the subtracts, right? And then these guys are doing the multiplies. Okay, so then in the first warp, in the first pass through this warp, the SM is actually going to run only the threads doing the addition. Okay, so 3, 0, 3, and then 6. Okay, in the next iteration, it's going to do the ones which are doing the subtraction, right? So 1, 4, 7, and then it's going to do the other threads. Okay, so it's going to take 3 passes. So it'll be 3 times as slow. So this is why you don't want warp divergence. Okay, because what could have if these guys all did the same thing, it would have taken you 1 pass, and now it's taking you 3 times as much time. So in the worst case, all 32 threads are doing completely different things. So in that case, it's going to take you 32 passes instead of 1 pass. Okay, you'll get a slowdown of 32 times. Okay, so let's see a practical example of divergence. So we're going to look at a problem, look at this reduction problem. Okay, so reduction, remember we talked about this in MPI. Reduction just means that we take a bunch of values and you add them all together. Okay, so how do you do reduction? Well, a simple way is using a reduction tree. Okay, so the way this works is that suppose you have a bunch of threads over here, right? They each start with a value. Okay, so the reduction tree is that we're going to pair up these threads, okay, and then add up their values. So initially, we're going to pair threads 0 and 1, right? So they're going to take their values and add it together and then store that in thread 0, okay? And then threads 2 and 3 are going to take their values and add it together, and then thread 2 will be storing that value, right? Threads 4, 5 get paired, 6, 7 get paired, and so on, okay? So initially, we pair every other thread, okay? And then next, we pair threads 0 and 2. So now we have parts of this reduction stored at half of the threads. Okay. Now we're going to start pairing up these half of the threads that have part of the answer. Okay. So we pair threads 0 and 2, right? And then 4 and 6, and then 8, 10, and so on. Okay. So then after this, we have a quarter of the threads, and they each have the sum of 4 values. Okay. So now we pair every 4th thread, right? And then we add them up, and now we have an 1/8 of the threads, each having the sum of 8 values. Okay, and we keep doing that. So each time we reduce the number of threads by a factor of 2, right? And then each surviving thread has doubles the number, the size of the sum that it has. Okay, so therefore, if we have n numbers to begin with, right, then after log n of steps of this, then we have one thread having all of the sum. Okay, so this is how we do the reduction. Okay, we're going to do log n iterations where in each one we pair up some threads and then add together their values. Okay, and then one thread keeps that sum, and then the other thread can become idle because it doesn't need to do anything else. Okay. All right, so this is actually code for doing this. Right, so what's happening over here is that so we have this variable called stride over here. Okay, so stride is like controlling which threads we pair. Okay, so initially we're going to pair like adjacent threads, right? And then so the distance between the paired threads is 1, right? Like we pair 0, 1, and then 2, 3. Okay, and then next we pair threads which are distance 2 apart, right? So we pair 0, 2, 4, 6, and so on. Okay, and then after that you pair threads which are distance 4 apart. Okay, so that is a stride, right? It's like how far apart is your partner. Okay, and you see that the stride doubles every time. Okay, so we're going to run a for loop for basically log n rounds, where in each round or each iteration, the stride is going to double. Okay, and in each round, what we're going to do is we're going to take we're going to take the threads whose such that if you take in modulo 2 times the stride. Okay, so initially when your stride is 1, right, you want to take the threads 0, 2, 4, 6, 8. When your thread is 2, right, stride is 2, then you want to take the threads 0. So this guy is going to do an addition, right? When stride is 2, so here's stride equals 2, right? Then you have threads 0, 4, 8, and so on, doing the addition. Okay. So, anyways, so the only active thread in an iteration is if your thread ID modulo the 2 times the stride is equal to 0. Okay, if it's divisible by 2 times the stride. Okay, and when this happens, then this thread is gonna take its own value, and then also take the value of its partner, which is stride distance away, and it's gonna add that up and store it in itself. Okay. And now the sync threads, the reason we need this is because we need to like complete all of these sums in the first stage. The first stage is over here, right? So we need to complete this entire first stage. This entire first stage before we start the second stage. Okay, you don't want to mix up these stages. You don't want to run them concurrently. Okay, so that's why if you do a sync threads here, what that's going to do is it's going to make sure all of these threads have finished summing at this stage before you go to the next iteration of the for loop, where you do the next stage. Okay, all right. So this is just explaining what the algorithm does. Now I claim that this algorithm actually has warp divergence, and the reason is that the reason is that we have this if statement over here. Okay, so this if statement splits the threads up into 2 types, right? So there's this one type that's doing the addition, right? So for example, this thread is doing the addition, and this thread is these threads are doing the addition, and then the other guys are not doing anything, right? Because they're just like sort of the partner that's going to become idle. Okay, right. So therefore, since you have these 2 types of threads, right, then instead of running this running a warp in 1 pass, you need to take 2 passes. Okay, so this is working sort of twice as slow as necessary. Okay, so now we want to see how we can mitigate this issue of divergence. Okay, so what we're going to do is we're going to change the algorithm a little bit. Okay, and this new algorithm is going to have a lot less divergence. So the way this works is in the original algorithm, you first, so you keep picking these partners, right? And the partners are always a distance of stride away. And the distance is going from 1, right? So here the distance is 1, right? And then you go to 2, and then 4, and then 8. So the strides are increasing, right? Now, you could also do reduction another way, where you make the strides decrease, okay? And that's what's being shown on this right over here, okay? So what's happening over here is initially you don't pair 0 with 1. You pair 0 with, let's say you have 512 numbers that you try to add up. Okay, so then you pair 0 with half of the numbers that you're adding up. Okay, so 512 divided by 2 is 256. So you pair 0 with thread 256. You pair 1 with thread 257, and so on. So initially your stride is 256. Okay, now after you do this first phase, what you have is you also reduce the number of values you have from initially you have 512 values in the first row, and after you run this first phase, you end up with 256 values. Okay, now now that you have 256 values, you're again going to partner up the nodes which are distant half of 256 apart. So now the stride distance is going to be 128. Okay, 128. Okay, so and now that's going to reduce these 256 numbers down to 128 numbers. And then next, you're going to pair guys which are distance 64 away. So now here you see that the stride is reducing by a factor of 2 each time, as opposed to the previous one where they were increasing by a factor of 2. Okay, now I claim that this new algorithm, so first of all, this new algorithm works correctly, right? Because eventually all these threads are going to combine into one thread, and that guy's going to have the sum of all the values. Okay, so this is a correct algorithm, just like the previous algorithm, but it's going to have a lot less divergence. Okay, and the reason is that if you look at, so let's look at the first iteration. Okay, so here every thread is saying that, so this is the new algorithm over here. Okay, so now if you look at a warp of threads, let's say a warp of threads only has 4 threads in it. Okay, so let me switch to blue to make it easier. Okay, so all right, so to switch it to blue, so let's say that you have so this is going to be a warp of threads, and then this is some other warp of threads. Okay, now you see that the first warp of threads, okay, they're all going to be doing the same thing, because if you look at this instruction over here, right, every since initially your stride is 256, okay, then if you look at the first well, I guess let's just look at the first 32 threads in the warp. Okay, you see that all of them, the first 32 threads all satisfy this condition over here, right? Whereas for the previous algorithm, if you look at the first 32 threads, right, half of them satisfy this condition, but half of them do not satisfy this condition. So there were 2 branches in the first warp for the first example, whereas for this new example, there is just 1 branch, because all 32 threads in the warp satisfy this condition. Okay, now you can look at the next warp. So the next warp is going to have consist of threads 32 up to 63, right? Because it's 32 threads per warp. They're also all going to satisfy this condition, right? Stride is 256, so this entire warp satisfies the condition. So there's no divergence in this warp. Okay, for the next warp, right, that is, what do we have here? 64 plus 32 is going to be 95, right? All those threads also satisfy the first, this condition. Okay, now eventually you get to, let's say, what is it, the 8th warp, right, or the 9th warp rather, okay, that is going to be threads 256 up to, what is this, 287, okay, right? Now all of those threads, right, you see that all of them are larger than stride. So all of them do not satisfy the condition, okay? So what I'm showing here is that for all of the warps in the first iteration, okay, they either all satisfy the condition or they all do not satisfy the condition. So therefore, there's no branch within the warp. Okay, there's only a single branch within the warp. Either you do this instruction or you don't do this instruction. Okay, so there's no divergence in the first iteration. Okay, now in the second iteration, right, what's going to happen? This stride is going to become 128. Okay, so that now you can check again that, for example, threads 0 to 31, right, they're all less than 128. No divergence. Okay, threads 32 up to 63, they're all less than 128. No divergence. Okay, threads 128 through what do we have here? 159. Okay, right? They're all larger than stride, so no divergence. Okay, so in fact, you can go ahead and check that as the stride decreases, it's only when you get down to the stride being 16, okay, that you could get any divergence. Because once the stride is less than 16, then for the first warp, half of the first warp is less than 16, and the other half is larger than 16. Okay? Right. And as the stride gets smaller, you also have divergence. Okay, but we've managed to get rid of the divergence for many of the initial iterations. Okay. Yeah, and then in fact, you can try to think about whether there's some way for you to get rid of the divergence even in the last 4 iterations of this code. Okay, so now let me try to finish up here. So the final thing we're going to talk about is bank conflicts. Okay, so bank conflicts. This is something that occurs in shared memory. Okay, so coalesce accesses is for global memory, and bank conflicts are for shared memory. So the thing is that the shared memory is it's arranged into blocks. Okay, so we have 48 kilobytes, and they're arranged into blocks, and they're arranged into banks. Okay, sorry, they're called banks. So a bank stores a set of memory addresses. Okay, and then a bank. Let's see. Okay, so different banks can access. Threads can access different banks at the same time. Okay, so for example, if you have 4 threads and they want to access these 4 banks, right, they can do that simultaneously. Okay. However, if you have 2 threads that try to access the same bank, okay, so suppose you have one thread that tries to access this piece of data and another one that tries to access this piece of data. Okay, now if these 2 pieces of data are stored in the same bank, right, then you get a bank conflict. Then you cannot make these accesses simultaneously. You have to do them sort of one after another. So now it takes you 2 time steps to do these accesses. Okay, so yeah, so currently, let me switch back to red over here. Okay, so currently so here I'm showing 4 banks, right? So all the shared memory is being divided into these 4 chunks. Okay, now in practice, current GPUs have 32 banks. Okay, so we have 32 of these rows over here. Okay, and you can figure out exactly where an address is stored, which bank it's stored in. It's simply the address modulo the number of banks. Okay, so basically the address modulo 32. Okay, so as I said, if the threads within a warp, okay, so if they access different banks, then it just takes 1 pass to do this. Okay, so if they access banks 0, 1, 2, 3, it finishes in 1 pass. Okay. However, if you have multiple threads accessing the same bank, okay, if you have, let's say, 3 threads accessing the same bank, okay, then you get a k-way bank conflict, and now the accesses take k passes to finish. Okay, so k times slower. Okay, the only exception is if all these threads, if they access the same bank, but it also happens to be the same value. Okay, in that case, the value gets broadcast, and then all these accesses still finish in 1 pass. Okay, but if they access the same bank and they're different values, then it's going to take k passes. Okay, and also this is only applying for one particular warp. Okay, if the threads from 2 different warps try to access the same bank, that's not a bank conflict, right? That will not cause a slowdown. Okay, so now let's look at an example of a bank conflict that can occur in practice, and also let's see how we can solve this problem. Okay, so suppose we have 4 banks. Okay, so these each color is a bank over here, right? And then suppose your warp only has 4 threads. Okay, and suppose our block size is also 4 threads. Okay, now let's say that what we want to do is we want the threads to load 2 values from global memory into shared memory. Okay, we want each thread to load 2 values from global into shared memory. Okay, now one way that you can do this is, well, thread 0 can load, so here I've labeled the memory locations, right? So 0, 1, 2, 3, up to 19. Okay, so one way to do this is just thread 0 is going to load memory location 0, 1, right? Thread 1 is going to do 2, 3, right? Thread 2 is going to do 4, 5, and so on. Okay, so 2 each. Okay. However, if you do it this way, right? So the way to do this is, so initially thread 0 is going to read location 0, right? Thread 1 is going to read 2, right? Thread 2 is responsible for 4 and 5, so it's going to read 4 initially, and then 3 is going to read 6. Okay, so here's the code. And now if you look at it, if you look at the accesses they're making, you see that in the first instruction over here, okay, you have a bank conflict between threads 0 and 2 because they're both accessing the red bank and different elements in the red bank. Okay, and also you have a bank conflict between 1 and 3 because they're both accessing the green bank. Okay, so now these instructions are going to take 2 passes to finish. Okay, each of these is going to take 2 passes to finish. Okay, sorry, that's just the first instruction. On the next instruction, right, you see that thread 0 is going to access 1, right, but thread 2 is going to access 5. So now both of these are in the blue bank. So again, you have a bank conflict. Okay, and same for the other threads. They have a conflict in the yellow bank. Okay, so therefore this instruction takes 2 passes to finish because of the bank conflict, and same here. Okay. Now to get rid of this bank conflict, there are various techniques. So later on we'll see something called padding and some other techniques. But here there's a very simple way to get rid of the bank conflict, which is that instead of having thread 0 access 0, 1, right, and then thread 1 doing 2, 3, right, instead we're going to have thread 0 do 0, 4. Okay, it's going to access these two. Okay, thread 1 is going to do 1, 5. Okay, so we're just going to change the order that the threads access the data. Okay, so now you see that what happens is in the first iteration, thread 0 is going to read its 0, thread 1 is going to read the 1, right? 2 is going to read 2, and so on. So now all of these accesses are to different banks, and there's no conflict. Okay, on the next iteration, right, they're going to read 4, 5, 6, 7, and again, there's no bank conflict. Okay. So yeah, so this is just an example of bank conflicts which can occur, which can really hurt your performance. And there are often ways that you can somehow get around these bank conflicts by sort of reordering, either reordering your operations or sort of changing how your data is laid out. Okay, that can also help you avoid bank conflicts. Okay, so so that's all we're going to talk about for this lecture, and so next time we're going to continue with more stuff about GPUs.